To collaborate efficiently with robots, we need natural language interfaces which are grounded in the physical world. There has been a lot of research in the robotics community on building models for robot instruction following. Most of these contemporary approaches reason in the context of rich and static models of the world. This allows them to interpret instructions that require knowledge of the current state of the world. However, it prevents them from understanding instructions which require knowledge of the past dynamics of the world. Bridging this technical gap involves non-trivial challenges pertaining to both world state estimation and language grounding. In this work, we present an approach called Language Guided Temporally Adaptive Perception (LGTAP) for enabling efficient language grounding in cluttered dynamic worlds. In our work, we use distributed correspondence graphs (DCGs) for performing language grounding. DCGs build a factor graph on top of a sentence constituency parse. Each factor in this graph connects a sentence phrase to a symbol using a binary correspondence variable. Symbols are constructs representing viable meanings for that phrase. DCG then frames the problem of language grounding as a search for the most likely set of correspondencies that maximize this factored distribution. To interpret instructions which require knowledge of the past dynamics, we can perform DCG inference in the context of a dynamic model of the world. However, constructing a model that tracks the state of all objects at all times is computationally intractable. Therefore, we hypothesize that there exists a temporally compact model of the world which tracks the state of only the task-relevant objects and only to the required extent which is sufficient for inference. To build such compact models, we introduce the concept of grounding constraints. On a high level, grounding constraints are rules regarding what should be the output of the language grounding model. For example, the grounding constraint for the sentence, "the cube that was on your left," states a rule indicating that there exists only one symbol in the inferred groundings, gamma sub t, representing an object of type cube. We then use these grounding constraints to close the loop between grounding and perception in our intelligence architecture. Given an instruction, the architecture first generates grounding constraints for it. Perception model that captures the current state of the world. The grounding inference is then performed in the context of this world. Validity of the inferred groundings is then established by checking if they satisfy the corresponding constraints. In the case that the constraints are not satisfied, a request is sent to the perception module for providing a state of the world from time t-1 to t. This cycle continues until a temporally compact model of the world is constructed which contains just enough dynamic information for accurate grounding. To make the perception and grounding runtime efficient, we adopt two techniques. First, we make perception faster by leveraging the information in the instruction to model only the task-relevant objects. Second, we perform efficient graph updates, which allow for selectively recomputing only the world and children-dependent features in DCG and reuses the prior computational effort to speed up the grounding runtime. This figure shows proposed intelligence architecture, which closes the loop between grounding and perception by using DCG in three different ways. To evaluate the performance of LGTAP, we assess its impact on the world model compactness, grounding runtime, and grounding accuracy, respectively, with increasing degree of clutter in the world. For generating the training data, we first created 10 unique tabletop scenarios using a gazebo simulator and introduced dynamics in it by rearranging the objects. We then generated a training corpus of about 200 instructions in the context of these simulated worlds. These instructions were annotated separately for the three unique language models used in the architecture using the corresponding symbolic representations. Test data consisted of a total of 96 utterances collected in the context of 8 unique tabletop scenarios in the real-world settings with increasing number of objects. Each video clip was 3 minutes long. LGTAP creates cardinally and temporally compact world models and maintains similar runtime to the exhaustive baseline. It also improves grounding accuracy, especially in the cluttered worlds. Unlike the baseline, LGTAP's perception rate doesn't decrease as the number of objects in the world increase, enabling it to make accurate world models of dynamic worlds. Here is a point cloud visualization showing a human collaborator rearranging various objects on the table. Here is the visualization of the lazy backward search enabled by LGTAP for the instruction "the box that has 2 cubes." Here's another example showing the backward search for the instruction "the box that has 3 cubes." In contrast to the previous examples, here is the visualization of the inaccurate world model generated by the exhaustive baseline for the same instructions. This video shows a robot demonstration in two different scenarios for the instruction "point to the box that has 2 gears." Thank you for watching this video.